Now we want to calculate the coefficient of determination, or the r-squared value, and that's given in the book as a formula, SSR over SST. Now SSE, SSR, and SST are going to be important components for us to do the statistical analysis now and later, and they're given by the following formulas. There is a little discussion in the content of this module explaining some of the reasoning behind these formulas and what they're used for. So be sure and read that. But right now, let's just try to calculate the values. You'll notice that SSE and SSR depend upon the estimated regression equations output for each of the x sub I values. In other words, we need to calculate a column of the estimated values, and then we're going to need to subtract those from the individual y values in the SSE formula, and then we'll have to take those values and square them. And then we'll have to find the difference between the estimated values and the y average. And we'll have to take those values and square them. And then finally, we need to take the difference between the individual y values and the y average, and then finally square those. And once we do that, we can add them all together according to the formula to get our SSE, SSR, and SST. So let me go ahead and take each of the x values and plug them into our regression formula that we've already created and fill out that column. Okay, I get, for a value of 68 plugged into my formula, I get 133.5 pounds. For a height of 64 plugged in to my formula, I get 111.5 pounds. The 62, 65, and 66 I've recorded there. Now I need to subtract these values from the output values of the equation. In other words, trying to find the difference between the actual data point weights and the weights that would be predicted by the equation or formula that I created. So 132 subtract 133.5 would leave me with a negative 1.5. 108 subtract 111.5 would be a negative 3.5. And then for the others, I'll have a positive 1.5, a negative 2, and a 5.5. Now I'll need to square these values, and I get 2.25, 12.25, 2.25, 4, and 30.25. Actually, at this point, I can go ahead and add these up, these square differences. And I get 51. So I've actually calculated SSE is 51. The next thing to do is to take the estimated values and subtract the average from each one, the y average or y bar. So in my first calculation in this column, I'm going to take 133.5 and subtract 117 to get 16.5. And then I'm going to take 111.5 and subtract 117 to get a negative 5.5. And then continuing to do everything in a like manner. And then I'm going to want to square these values. So 16.5 squared is 272.25. And then the negative 5.5 squared is 30.25. And I have another 272.25, a 0, and then another 30.25. At this point, I can go ahead and add these together. So the sum of the estimated values subtract the y-averages squared would be equal to total of 605. So now I've basically calculated the SSR, and I got 605. We've already calculated in the first part of this problem the y sub I minus y bars, but those were 15, negative 9, negative 15, negative 2, and 11. And then I need to square those. I get 225, 81, 225 again, 4, and 121. So adding those together, I would have a total of 656. So SST would be 656. Now in the textbook we see that and if you think about the values that are being combined here, that SST is equal to SSR plus SSE. And to check that out, we can see that 51 plus 605 is 656. Now the value of this last formula here is that if you have any two of these, you can always easily calculate the third one. If I just calculated SSR and SSE, then I could add them together to get SST. If I just had SSE and SST, then I could take SST subtract SSE and get SSR. So this little formula down here at the bottom will allow you to get one of them if you have the other two. Now, the coefficient of determination finally is SSR 605 over 656. So calculating that, I get about 0.92. Now on a scale from 0 to 1, a 0.92 would be considered a very good fit. That the regression line that we created and graphed with the data would be considered a very good fit at 0.92. The closer you are to 1, the better the fit. The closer you are to 0, the worse it is. Now we're going to analyze that further in the next section. But the R-squared value does give us a feeling for how well the line fits the data set. Also read the content portion of the module here to discuss this issue further. And another interpretation of the R-squared value, or maybe another way to say it, is that 92% of the total sum of squares can be explained by using the estimated regression equation, as opposed to just making a prediction of the women's weight by finding an average. Now you really want to make sense of this. Continue to, again, look at the module and read carefully the interpretations for the R-squared value. One other comment I'll make is that the R-squared value really doesn't give us a test for significance. Although it tells us how well the line fits the data set, we're going to need to analyze the regression equation further. So that will be in the next section or two.